Okay, why does it do not work? Yeah, better do that. And which hospital did you go to?
Tri-Service General Hospital.
I don't know that.
I went to the.
I mean, they could be very good. I have no idea.
I just went to the dormitory counter
Ah, okay.
downstairs.
Yeah.
Austin told me to go there.
I mean, I have to go to the hospital on Thursday. And the doctor there, his English is also very good, but he's a heart specialist, so probably not what you would be looking for. Then what we want to do today is I let's look first at forward kinematics and yeah. So here we already set up a small Mujopo environment that we can load. And I think I showed it last time. now it works. Here we have the Taiwan Bear robot after it crashed. So I can reload it and then flop. Because it has no control yet. Right? It falls down. And here we have the OP3 robot. So this is working. Now, for humanoid robots and all other types of robots as well, um, once you build it, you want to control it, of course. In order to do anything but the most primitive motions, where you just want to see the joints move at all, independently of what effect they have, you do need to be able to at least understand the geometry of the motion. So if you want to follow a defined path, then you need to have the inverse kinematics. Um, in some of the industrial, like a Cartesian robot, where you just have two linear actuators, X and Y, and it moves like a plotter. Okay, there the kinematics are very easy. You just go to X location and Y location and it moves in a straight line. But anything with revolute joints where you need to do rotation and convert it into motion, you need to understand the kinematics. Actually, to solve that particular problem, if you have a robot arm and you want to draw a straight line, then you need to know the inverse kinematics. But at a minimum, you need to know the forward kinematics so that you can figure out where the robot is in space. And that would be the first part of the problem. So we'll be looking at kinematics, and I think we did this last time already, but here's the upper body of the OP3 robot in 2D. So that's our very large humanoid robot, the one that drives the scooter. Or for the robot that you build yourself, the little leg, half of the robot that you build yourself. For that kind of robot, first of all, what is the forward kinematics problem? And then how do we solve it? So what do we mean when we talk about forward kinematics? What's the input and what's the output? Yeah?
The input are angles and or joint angles, and the output are Cartesian coordinates.
Yeah. So that's right. So the input is going to be what's called the joint configuration. If it's a revolute joint, it would be an angle. If it's a linear actuator, it would be a displacement. And the output would be, for some kinematic chain, usually the end effector position in the world space, right, in the world coordinate system. With humanoid robots, there's kind of like two levels, because there are any kind of movable base, any kind of robot that can move through the environment, you sort of have the space relative to the robot, so where the arms are relative to the torso of the robot, and then you also have the position of the robot in the physical world. So there's kind of a two-level process for doing it. Now, how do we solve that?
To define transformation methods.
Right. We looked at homogeneous coordinates, right? And the way that we model translation and rotation is using homogeneous affine transformations and transformation matrices. Now, these transformation matrices in 3D space are 4x4 matrices, right? So we need to extend our coordinates into homogeneous coordinates. So we have like kx, ky, kz, and then k. That allows us to add a constant term to the translation. That's what we need for the translation. And then once we have these transformation matrices that go from one joint to the next, then we can calculate what the compound transformation is. Right? Because everything is a 4 by 4 matrix. If you left multiply them, you end up with the position of the end effector, assuming that, yeah. If you multiply the points by the matrix and you keep left multiplying it, then that's the transformation that you end up with. So the whole point boils down to transformation matrices and the compounding of these matrices. We have modeled rotation and translation. That's all we need for this type of robot, right? Because the transformation that we described, let's say from this joint to the shoulder joint here, that's the next joint in the action, then that can only be a translation and then a rotation of the actual servo motor. And the translation is due to the link, and the rotation would be due to the motor, to the joint there. And if we have a displacement, a linear motor, then it would be a translation. That is what is changed by the joint. Now we have that. We now need to figure out what these transformation matrices are. Once we have those, then we can at least solve the forward kinematics problem. Right? Then I can set joint configurations, and then I can figure out what's the world coordinate of the end effector. So how would we do that? The other thing, I guess, that I wanted to mention is the transformations that we're interested in are, as far as the kinematics are concerned, are only concerned with the position of the joint. So if I have a robot that has a revolute joint here, and then a link, and then there's another servo motor here, another revolute joint, with another link, then in that configuration, the end effector, yeah, that's actually, here's another joint, okay? The end effector position is this position here. Now, if my link looks like that, right, then that doesn't actually change anything as far as the kinematics of the end effector are concerned. Right? So the link doesn't need to be in a straight line. The actual shape of the link, the actual shape of what connects joint 1 to joint 2 doesn't matter. I can make it like this, or I can make it like that. And all of these links are going to rotate around this point, and the position of J2 is not going to change. The position is going to change if J1 rotates, but it doesn't depend on exactly the shape of our link that we're following. So as far as the kinematics are concerned, the only points that we need to worry about would be the and then the position of the first joint relative to the origin, right? Or relative to the previous joint. If the torso looks like that, or it's wider, or goes up high and then comes down to there, none of this matters. All of this would matter if you calculate collisions. If you want to detect collisions, then of course it makes a difference. Right? But just in order to figure out the position of your end effector, the actual shape of the link doesn't matter. Here, if you want to control it, you must know the effect of the control. We can have simple degree of freedom controllers, revolute joints for rotation. It's the most common one. We can also have linear actuators. And now I don't get the video anymore. It would be, I wanted to show this video. Yeah, this will be a task where kinematics are very important. The robot is typing on the keyboard. So we need to know where the fingers hit. So we need to describe the cumulative effect of the set of joints, and the joints are grouped into kinematic chains, so that we only include the joints that are actually have an impact on the position of the end effector. So for most humanoid robots, that will mean that we have 5 kinematic chains: a right arm, left leg, right leg, and a head. And we now come up with a number of conventions. Those are not strictly necessary, but they simplify communicating with other researchers about your kinematics, and they help you sort of understand easier what you're talking about. Like for yourself, you organize things easy. So we have with a robot that has n joints, we have n plus 1 links. The joints are labeled starting at 1, which is very unusual for computer science, but that's what we do, and they go to n, and the links start at 0 and go to n. So that's how we have 1 extra link. Joint K is the one that connects link K minus 1 to link K. And we go out so we increase the joint number as we go along the kinematic chain, which means that joint K does not affect the position of link 0 to K minus 1. It will only affect the position of link K, K plus 1, all the way to n. And then we assign a joint variable to each one of the joints. Either theta, an angle, if it's a revolute joint, or displacement, if it's a prismatic joint. Now, to find the location, we attach a coordinate frame. That coordinate frame can, in theory, be attached anywhere we want, but it makes things a lot easier if you also follow systematically um, some sensible notion about how to apply those coordinate frames. And for a 2D manipulator, this is what it would look like. We have an initial coordinate system, also called the inertial frame or the world coordinate system, uh, that moves us to joint 1 then, joint 2, joint 3, joint 4, joint 5. And link 4 is between joint 4 and joint 5. And link 2 is between joint 2 and joint 3 in our kinematic chain. Now, these red-green arrowed coordinate systems for each one of the joints, we could place them anywhere, but it doesn't really give us an advantage. Then the motion becomes much more complicated. So to simplify things, one of the conventions is that the z-axis is the axis of actuation for a joint, and for a revolute joint, that means that the axis that we rotate around, so we always rotate around the z-axis from x to y in the positive direction. So the z-axis will be pointing out here. And if it's a linear motor, a linear actuator, then the z-axis will be the axis that we move in, that we do the displacement in. So we align the z-axis with our axis of actuation with the joints. And that then has advantages. The biggest advantage is that now, if I move this coordinate system here, then any kind of rotation would be, I would have to translate it, rotate it, and then translate it back. So it would be much more complex sort of to think about, to visualize what is going on. And now if we have the z-axis there, then at least we know this is going to look, the first part is going to be a rotation around the z-axis. It doesn't mean, it doesn't completely specify the z coordinate system, because even if I say that z is the axis of actuation, I still have a lot of flexibility where I put 0. Like anywhere on this axis, I could put the coordinate system, right? It doesn't have to be at the horn of the servo. And in fact, if you follow the Denevit-Hartenberg convention, which is a more stringent convention that I introduce here, I'll talk a little bit more about later. If you follow that, then most of the time it's not where the servo horn is. I like to have it where the servo horn is for humanoid robots. That usually works quite nicely. And also we could have Z pointing inside of the paper or coming out of the paper. Both of those, the joint would still be rotating around the Z-axis. So it's not like you have no choice there. So we have the transformation matrices. We need to find the transformation from coordinate frame OI minus 1 to OI. And that transformation matrix depends on the joint variable as well as the following link that is attached there. So we define transformation matrix Tij, which is the transformation from joint I to joint J. If I and J is the same, it's just the identity matrix. Otherwise, it's the transformation of joint I plus 1, I plus 2, all the way up to J. If I is less than j, and if I is greater than j, then it's the inverse of that transformation. Now, it is practically quite easy to work out these transformation matrices, and that's what I want to do today. Um, for a humanoid robot like that. If we look at the 2D case here, or even the 3D case for the robot, then we have some coordinate system, OI minus 1, and now I need to model to OI, which is a different kind of coordinate system. And we have x, y, z, and x, y, z, y, z, x, y, z. Okay. So then that I can break down into a translation, right? And the rotation that says, so from here to there, I would have to rotate around the x-axis this much, and so this would be theta here maybe, and we also rotate around x this way, and then I rotate around x another 90 degrees to bring the z-axis up and the y-axis 20 backwards, if that's the transformation we have. Now, that means we should be able to represent our transformation matrix by some translation and some rotation. So what you would expect from homogeneous coordinates would be that we do the translation first, and then I was very insistent that it's important that you realize that you need to rotate, the rotation matrix must be left multiplied, right? And that makes sense because we have the points, we multiply by matrix 1, then by matrix 2, matrix 3. And matrix multiplication is not commutative, so R times T is usually not the same as T times R. However, when you see this written in the textbooks, this will look like this. And I think that's probably the only interesting problem in forward kinematics. If you can understand this, then you can work out the kinematics quite easily. So why is it the other way around? Why do we have to write multiply here? Yeah?
Because we go back to the origin, then rotate it, and then rotate.
Right, because we are rotating, exactly right, we are rotating around this point, right? We move to there, and this is where we want to rotate around, right? So in order to be able to do that, our rotation matrix only works around the origin, right? So for this rotation, what I need to do is I need to this is what we want to do, right? So we want to do a rotation, but this is a rotation around this point T. So in order to be able to do that rotation, what do I have to do? I translate, right? Then that's my rotation point. Then I need to take that point, bring it back to the origin, which will be t minus 1, right? The inverse of t. Then we rotate, and then I translate it back. So then with associativity, I can write it like this, which gives me PR, right? So it just works out that way in this particular case. If you always want to translate and then you rotate around the point that you translated to, this is what you get. So in order to work out the kinematics for a humanoid robot, I usually just assign the coordinate frames to where I want them to be, calculate the difference between the two frames, and then do the rotation. And that's a transformation matrix for joint 1, and then joint 2, joint 3, joint 4, so on and so forth. Also, those transformation matrices also have to be right multiplied for the same reason as this one. So if you do it step by step, it is not so hard to work out the forward kinematics. So here this shows R1, T1, but I don't want to rotate around the origin. I want to rotate around this point. So then we expand that and end up with T1, R4 in this case. So O n will be the position of the end effector in the inertial frame. That will be a 3x1 vector. R0 is the change in orientation. You end up with this kind of rotation matrix. Then we calculate the cumulative effect of all of those. So A1, A2, A3 up to AN, which can be, the resulting matrix can be broken down into a rotational 3x3 rotation matrix and a translation vector here. And these rotation matrices, they consist of just the rotational part, which means they describe the relative orientation between the two frames, and the origins tell you the displacement, the distance between them. Then here would be an example of a simple leg for humanoid robot in the sagittal, in the lateral plane. We can calculate that. So here our transformations are, we start with the initial matrix, then we translate, which is our initial link. Right? There's no rotation yet. And then we rotate, then we translate. And then we rotate around. Sorry, this is A1 and then A2. So translation, then rotation. Translation, rotation. So here I have joint 1 at this location in the origin here, so the initial translation would be that. And then probably the thing is visualizing this is very tricky with the different coordinate frames. Especially because you have two hands, but only one gives you a right-handed coordinate system. So thinking about that is actually really quite difficult. So if I work on a kinematics problem or any other kind of problem like that, then nowadays I just like to use a matplotlib and I draw the thing in the 3D space. Then you can rotate around and that'll make things a lot clearer. And then here would be Python code to calculate the forward kinematics, the set of links and the thetas and the um, translations and rotations for 2D. Then I can calculate that for any job. Oh, I must have missed some library setup. And this, by the way, works in 3D just as well. Oh, I didn't. Oh, that's why. Okay, so for our, let's see if I got a message. Um, Now we want to build on for our rock climbing robot. for the leg, for example. And now we want to implement the forward kinematics, right? Uh, so if you have your leg here, then you can work on that. Otherwise, you have to guess some numbers and then fix them later on. Oh, holy cow! Like a tree. Was it just me that saw it? A tree just fell down.
Just so true.
Yeah. Wow. No, 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 nobody jumped. Yeah, yeah, this thing there. Well, that was pretty scary. Wow. Very huge, yeah. Holy God. I'll be my own doctor. You just missed the excitement.
What happened?
The huge tree fell down from through, and I just saw it fall in the window, and a little bit spooky. Okay, so the good news is once you have forward kinematics, you can at least approximate inverse kinematics very easily. Um, if then you can use the Jacobian inverse or Jacobian transpose methods, and that'll give you a good solution to the inverse kinematics. That may be all you need. Sometimes, if you are limited in the processing power, then you may need to use an analytical solution. Sometimes you have a domain where you need to worry about singularities in your space. But for example, for walking gait, um, we deal with singularities, which means like the thing is not moving because you lock your joints by adding in constraints, like similar to what they do in animation software. So, for example, you specify that the knees on the humanoid robot always must bend forward, never the other way. Then that means that you get rid of that singularity at that point. Then you know which way to move. So this is a very short, brief introduction to forward kinematics. Now I've been thinking, and if you look at the Blender file that I have for the Taiwan bear and the other humanoids that I built, I actually have the Python script with this Blender file, and that actually generates the Python and TypeScript code to calculate the forward kinematics. Because from the Blender software, I can actually get the position difference, right, between the bodies, because I need to place the bodies, I need to place the joints, so I can figure out what the translation vector is, and I know what the rotations are. Otherwise, Blender wouldn't be, if Blender cannot draw it, it also needs the forward kinematics in order to be able to draw it properly. So my idea was that if I add that into the Blender program, then that's cool, and that usually works really well. So for example, here, So this one creates the kinematics files, forward kinematics.py and .ts for Python and TypeScript, which are the two languages that I use mostly for doing this kind of work. Of course, I could also easily do a C++ thing if I wanted to. Just haven't had the necessity to do that. Otherwise, I would add it into my scripts. And so then that's kind of nice, right? Then you just have your join, and I have this convention, and that actually cost me a lot of problems. But if you look at the model that I have, and of course this is all available on the GitHub, um, rock climbing, gym. If you look at the coordinates, then here I model the ball joint. So Z is always sort of the most likely axis of rotation during the motion. This is Y, this is X, so here I aligned it. But my hinge joints, my 1 degree of freedom, my actual revolute joints, I always set them up so that the Z-axis is the axis of rotation, and I set them up so that um, the home position is always 90 degrees, and they're all like that. So that's why the Blender file can automatically calculate um, the forward kinematics, because it now knows uh, what are the joints, because I label them. Like anything that's not R joint is not a revolute joint. So, and then if it's an R joint, then it will rotate around the local Z axis. So local Z axis and positive direction of rotation is the same as is counterclockwise. So then once I have the model, then the kinematics can just be generated. The code to calculate the forward kinematics can just be calculated automatically. Then you don't need to do anything. Now, if you use Katya and more complex software, then you can do the same. You just don't have to write the Python code to do that yourself. But I find that quite convenient. However, this year we have a little problem, right? Because oh, by the way, the Blender file also generates the Mujoko model that is loaded into the Mujoko simulator. But the problem is with these legs, I didn't design this one in Blender first, right? You guys just build it. So that means I can't run my software on there. So I think the right thing to do would be to actually use the Mujoko XML file to extract that information, because you want to simulate this one. So whatever you do, whether you like Blender or you don't like Blender, or whether you want to use Katya or whatever, eventually there has to be some kind of Mujoko simulation model for your rock climbing robot, right? So I want to today, for the rest of the class today, I think we're just going to try and implement extracting the model from Mujoko rather than Blender and calculate the forward kinematics.
Do you think that's what It needs to get the model into mutual code via the XML file, not model it first in Blender.
I think so, yeah. I don't think there's, I mean, unless, if you are very good in Blender, you could, then you could copy my code, you could run it. But if you are, if you haven't used Blender much, then you might as well just put it into Module. I think your construction is not that tricky, right? Plates and links, so I think that's fine.
I think we will redo this one.
Okay, something, just use something for today's class. Okay. You can also use the Blender Via model that is now in Moodle Code. Or actually the OP3, you can also use that. Both of those models are available. But I would like to get these models actually into Mojoko. I think that would be quite cool. So now if we look at the, and there's a couple of annoyances. Like one thing I can't figure out is, like this is clearly red, right? But when I ask it what's this color, then Blender tells me it's black. I don't know why. That's why if I import that model into Mujoko, it's always no color. So if we now look at the one bear, oh, and here the Blender thing also puts in a bunch of coordinate systems just to help you debug your code. The positions are given by the robot, and then the orientation matrices. And then here are the joints. Oh, and if you see here, the ball joint, the joint that can rotate in X, Y, and Z, all in one location, I just modeled that as three separate servo motors. One that can rotate in X, one in Y, and one in Z. And the important parts are the body and the joint specifications. So what I want to write is code that takes this XML specification as input and then generates the Python subroutine in order to calculate the forward kinematic. Yeah. Yeah, I actually have multiple for there. So okay, let me see what happens to our Australia students, the other Australia students. Okay. So here we're dealing with an XML file. How would we process that? Because what I need to do is I need to extract the body tags, right? The body elements and the joint elements in order to be able to link them up to calculate the forward kinematics. Um, but if you look at it, parsing that file is a little bit troublesome because we need to match the tags. Like here, body starts, and here's another body, and another body, and then there's a geometry inside. And another body, and then here all the bodies closing tags occur. So how would we process that? Yeah. Let's say you want to try and write a routine first that prints out all the important information from that XML file, from the Mujoko XML file, which means you want to print out every part of the body line here, and you want to print out every part of the joint. Those are the two types of entries that we're interested in order to calculate our forward kinematics. We don't do collision yet, so we don't need to worry about the geometry mesh there. Otherwise, if we wanted to do that, we would have to worry about that. Now, to do this correctly, you would end up with some kind of recursive parser, right? So you would have something like get all the lines. So with open F read encoding as F for L in F dot read lines if L dot starts with a bracket and body, then you create a new body entry here, else if it contains, and then yeah, you can pass in L, but basically you would have some recursive call here to parser, which generates the rest of the bodies then, else if joined, if it's a joint start, then you start a joint, which you add, else if the end of the body, then you return the body that you created, else if the ends of the joint, then you return the joint. And that kind of works, but it's still non-trivial to parse this because you may have comments, right, in your XML file. You may have a string of white space at the beginning, string of white space at the end. That would also make it more difficult to parse. Then you have to strip the line first to remove the leading um, white space and the trailing white space, because it's usually not L is equal to L dot strip. And that would work. Or you can use one of the XML parsing libraries that exist for Python, such as, you guys know, have you used any? Never? Never had to work with HTML or XML?
No computer scientists, so maybe that's why.
Pardon?
We are no computer scientists.
Oh, okay,
so maybe,
yeah.
maybe that's why.
Yeah. Okay. Well, you're lucky that it's not a really a nice. It's an okay format to generate a program to write XML, but writing it by hand is no fun. So yeah, there is beautiful soup. It's called beautiful soup. I don't know why. That one is the most popular parsing engine for Python. So you can use that. So you can import that. If I were to do that, that's what I would use. But maybe to show you this kind of pattern with the recursive parser, maybe I'll write it without the beautiful soup. So I have a. I thought I had a tools directory. And let's call it the Mojuko file parser file. And then let's just call it Mojuko file there.xml. Oh, I think I can just move. So here I'm just checking that I can actually open the file. Then this is So this should return um, a generator. So yeah, this returns all the lines if I want them to. So then, maybe we can try this one. Continue teaching. I don't have a microphone. Okay, nobody's there yet. Yeah, I'm not sure if that works. Oh, okay. It's not read line. I thought that was return the read line. Okay, so that works. Well, let me try again with 8 rounds. Yeah, that actually returns a list. So here we get the line. Now we can start our parsing. The other thing I need is I need to have my kinematics tree. And that I just built as a list. Actually, maybe I don't really need this one. I don't think I need this. I can just do it completely recursively. So then let's start our parsing. If L dot starts with, so this is the start of a body. And let's make them dictionaries. And then the parsing, I want to use regular expressions. So probably would have been a lot easier to use. I have this. And then body regular expression is equal to body length of L. Then we can say I, if L equal to space or Li equal to tab. How come? So now we're trying to parse the second part of the line. So here we found body. Now I need to extract name is equal to, position is equal, quaternion is equal. Right? And that's the kind of thing that beautiful soup does really beautifully. It just gives you the attributes. If I need to do that by hand, I need to actually start, go through, skip all the spaces, right? And then if I find something, I need to start adding it until I hit the equal sign. So this means we also need to have some state. Is there a holiday in Germany today?
No,
No, right?
there was one on Friday.
Oh, okay. Okay, if we're in currently state skip white space, then we're skipping white space. Else, set the state is equal to start attribute. Now I don't want to here, if I skip the white space, I go one character to the next. Here I don't. So if the state is equal to start attribute, so attribute is everything except white space or equal sign. I think I can do that. End is equal to while. So we can generate some character classes. So here, while it's white space, we skip it. Otherwise, we start the attribute, and the attribute, if it's not a white space, we add it. Otherwise, I just get rid of it. Or so here we can generate an error message if something doesn't parse correctly. autonomous robot. So here I want to only parse one line. Built-in function. Ah, strip. Index thing. Okay. Here we started an infinite loop. That's okay. I just want to. So here we found the name. Cool. That's correct. Then we need to look for the starting value. Now to start the value, we need to skip white space. How about we do it like this? Once we're finished, then we find the attribute. Uh, and here we skip, but not white space, but we skip until we have the start float. And then I need to pass in the end quote, and I don't worry about X errors or anything like that. You just hope for the best. And then let's see here. So let's see. Sorry. Where does it even print or found? Yeah. Attribute. We go back to attribute. Attribute name. That is oh, attribute name. Bias values. Body name equals to Attribute name is Taiwan there, and then here we have to skip on to attribute position 00 goes to 1, attribute opinions. So now I can extract the attributes and the values. And I'm just skipping the terminating bracket. So there would be here if L index is equal to the closing bracket of that line, then I break out a value. So we start a body. Maybe I just oh, okay, yeah. And body attribute is equal to value. And then here, let's not call it body, let's call it object. Here we're done. Body this, and result is body. Actually, I set it like that. Object. Because basically the parsing is the same if it's body or a joint, so we can do it like that. Oh, GJOINT. Hmm. So we have that. Now we return the object. And here we return the result from that line. And here I can do this. Join, so we can have the body here. And then let's see, object is this, going to object. Oh, that goes here. And then now I can extract the bodies and joints that I have, right? All of this work just to be able to extract this. So you can see how it becomes um, quite quite appealing to use a proper parsing library like Beautiful Soup. I'll just fix this so that I don't print them on all the time. If object is not none, and you print it out. So now I can get the joints and all that coming out here. And it does a okay job with with the what you call it, the parsing of the XML file. By the way, if you write this kind of code, I really cannot recommend it. What's the biggest problem with it? Like you can do this, right? You can sort of hack together a parser and it will extract the files that you want, but you really shouldn't be doing it. Certainly not for standards that are non-trivial like XML or HTML or anything like that, because guarantee the majority of security vulnerabilities, people being able to log into your bank account or um, um, what other bad things? Stealing your personal data. Most of it comes from people trying to do this kind of parsing because it's extremely difficult to keep track of where you are in the file and what you're currently looking at. And if you have a more complex format, especially one with XML, where the the data that you get here, right? There's really no extra validation that I input. Like for position, in order to get the position, I would split it and convert it into 3 floating point numbers. But whether those numbers make sense or not, I probably wouldn't be doing any checking on those. And so a lot of the vulnerabilities in modern software comes from people doing their own parsing and not checking error conditions correctly. For example, running out over the line so that instead of just terminating at the end of the tag, I simply keep going, right? So I may be reading some other stuff, by sending in an deliberately malformed XML file. So you upload this to the website and you want to, so this is a nice useful program. You think it's a great idea, I'll give this to my, put it on a web page, then people can upload it and they'll be happy because they get the forward kinematics back. But I mean, not if I do it, but if you do some, if you have enough customers, then somebody is going to try and figure out how to break this, guaranteed. And the parsing part is always where it breaks. Not always, but very often where it breaks. So then I'm reading past the end of the line, right? I read the rest of the text. Maybe the rest of the text, and I print out this is the position, and I expect these to be floating point numbers. But because the parsing doesn't actually check that it is a number, it may be overflowing and then print out passwords, for example, right? If that XML includes some other kind of secret information that you don't want to display to the user, they may trick you into displaying that kind of information. And that error is extremely easy to make because, as you can see, it's quite tiresome to do this kind of parsing. So everybody that rolls their own by hand usually ends up taking a lot of shortcuts. Assuming that the file is well formed, which usually a malicious attacker then can easily have a file that is not well formed, and then all kinds of problems occur. Lots of breakings via websites or web applications. Now, but for our purposes, this will be enough. So now you can see here if the attribute is equal to position, then the values are value.split on the space.
I can run my robot in Turbo, but it seems like no actuator. No actuator. It's a URDF robot arm. Let me see.
So see now our positions are this here.
It's using an URDF format file. It's like XML, but just not XML from Mojoko format. It's URDF format.
But can you have a look at it?
Yeah, there is a converter from URDF to Mujoko.
But I don't use any converter. It still can run. But seems like my robot arm it's no power, so it's just like this, no actuator. You don't know why?
Did you add the actuator?
No.
Yeah, you have to add them. Like there has to be a set of position or motor commands or whatever you can send.
Oh, why did you do this?
You have to. This is my project. You know
Oh,
that
the
robot
pass-
arm
the pass
is
zero.
yeah, by zero. I have to use this robot. So I just import this robot in Mojoko.
You can't control it.
Yeah. And why? Sorry, and why in the control I cannot control my joint? In the control menu Mojoko, I can't
You
see my
can.
joint.
You just have to give it the right values. So you need to set the amount of force that you have and okay, no, you didn't define any controls yet. You
No.
just defined the joints.
Oh, I don't have control. I just have the joint.
I mean, you don't have any motors. You have joints,
Uh,
which are like hinges, but no motor. You need to tell it that there is a motor there. So that would look like this. If you read the Taiwan Bear XML file, then that's what you have there. The actuators.
Ah,
oh my god.
If you don't have those, there's no motor, then it's just like. Right? So you still have to uh, generate those for your URDF file. And then depending on what kind of control you have, you can set here. You can set the KP, KD, and KI gains for the PID controller.
Do you need the ID controller?
If you have a position control, yes. It depends if you use torque control or position control.
I mean PID like for balancing, no, it's different.
Yeah, this
Like
is
our
different.
first
For the
assignment.
servo motor, right? There is a PD control loop running on the servo motor for each one of these motors. Because you tell it to go to 10 degrees, it needs to have a controller to move it to 10 degrees, right?
Oh, okay, I just know that. But we never define KP in simulation like gazebo Isaacson or Artis or Ross.
Then you
two.
use, usually you do.
Usually we don't do it.
Yes, you do it all the time. You have to do it.
Oh yeah?
Unless you use the default values that it gives you. But you definitely have to tell it whether something has a motor attached to it or not.
Every simulation.
Yeah.
Oh yeah.
Gazebo, Isaac Lab, all of them work the same.
Oh.
I just feel that Mujoko is actually quite nice and a lot easier to install than Gazebo or Isaac Lab.
Yes.
Like a 20 megabyte download and you're done. That's pretty cool for a simulation environment, especially because it can even use your GPU. If it finds your GPU, it uses it to do the rendering. So that's really kind of cool.
Is it works well with URDF or better to use Mojoko XML format?
Internally, I don't know, but there is a URDF to, there's a URDF exporter to Mojoko. Mojoko is a more powerful file format. So the contacts and everything you cannot describe in a URDF file, but you can describe them in a Mojuko file.
But is there a way of making the XML file dynamic? Was it just always when we change something here, we have to open the XML file, type in the thing?
So usually you need to have an XML file to define your simulation environments because it's impossible. It needs to pre-calculate like a ton of things to be able to be fast enough. So you cannot simply change the size of something, which would change the inertia matrix of the thing while it's running. You would have to stop and completely restart the simulation.
So we could not
So
out certain link lengths during the simulation by changing them in the simulation.
no, not the link length. No, I think that's not possible. So the way that we usually use the Mujoko file is what I did last class, and here in the Mujoko tutorial. There are some things you can change dynamically. Like last class, I showed um, the color. You can change the color of things because that doesn't impact the physics. So that's okay. So the way that you usually do it is you define your XML file in your Python program, right? And then you call Mujoko model from XML string. At that point, it generates the simulation environment. But before you call that function in Python, you can modify this file here. So if you want to have command line arguments for where to position it, or whether it's a sphere or a box, then you would just change that string before you call Mujoko from XML string. And then you don't have to open the file. So you can create this skeleton in your Python program as a string, and then modify all the stuff that you need to modify, and then start the simulation. But once you start it, then to change anything again, you would have to stop it and call this function again here. But then the simulation would restart. Like it's impossible. I don't think it'd be extremely difficult to restart the simulation in exactly the same state that you stopped it. I don't think you can do that. Like it would be like the robot jumps and all of a sudden you take away one arm and the physics are still supposed to work out that way. I don't think that is going to work. But usually we don't need to do that. Usually we have kind of the bear environment, and you can write the control, so you can make the bear jump and all of this in Mojoko after you started your simulation. So you have using the controllers, like anything in control, that's what you could control on the real robot as well. But anything that's not in control, you cannot really do. You already finished. Your control doesn't make him stand. No, these are the joints. This is the current state of the joint. You need to go to So now reload, pause it, and reload it. There, your arm moves. Pause it, pause, and reload. Reload, that is at the top. Then you can change the control, or no, then you can change the position of the joints. Or you can go up, go to physics, and then turn off gravity. You keep going up. No, up. Yeah, gravity. You click on gravity, then run. Now your robot is just hanging there because no gravity, right? You're always on the moon in the space now. And then you can move the joints, the control, you can see what the control is, because now there's much less friction. So yeah.
So does it mean the inertia is incorrect because when you run the simulation, the robot cannot balance itself because the center of mass is
Oh, it's on the
not correct.
impact. It's on the impact, and it doesn't do any controlling ability.
So the actuator, because the actuator,
The actuator is just fixed. It just drops down. There's no control. You set it to all 0 degrees, and in that state, it just falls over.
You should make it so it should always hang on the wall, right?
I think that would be easier. Yeah.
So you can also change this position.
Yeah, of
here,
course.
maybe from here.
So, yeah.
I'm trying to see there and move.
No need to walk.
Just
Just start. Just start there.
Oh,
Walking is in itself a non-trivial problem for small humanoid robots like that. So you want to change the starting position, and then move the joints to a reasonable position, and then you put the handhold there. That's easier than putting the handhold and then having to figure out at the beginning until you have fingers coming out. But yeah, good, nice. So you have your robot inside of Moodle. Yeah. So
where did you got the wall?
the wall is from yeah,
From your behalf.
in the gatehouse. Yes. Yeah.
So we do need to implement some camera, like
It comes
far
with
from the
multiple.
module.
You
You
can
can add camera.
yeah. You can add a camera. I added a camera in there somewhere. There's like a free camera, and then you can have some fixed position camera. Like the one that you can control with Mutual. I'm not sure if it always has that, or if it. I think that camera always exists plus the other ones that you define. So you want to define one camera that is looking at the wall at a 90-degree angle.
So later David will give the robot exactly same like this. Because it's
Yeah.
simulation.
That's space, yeah.
But it has to be similar, or I mean actually like this because in the simulation like
Well, no,
The
because
real
if he builds a
simulation.
different robot, he writes a different simulation.
The simulation that for robot doesn't break in real life.
Yeah.
So we can check first.
Yes, please don't try not to break my servo moves. So where's this? Where are these handles? Where did you place them? Where is it?
Maybe we don't need to
Out of this.
I think that's the
No, we need to.
prompt.
Yeah. I mean, you can have different colors. That's fine, but the first one we would want to climb, I think, is have 4 holes. The bigger. Yeah, yeah, four center holes. Center, 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 center. Three types of holes. So here we put center, 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 center. Then the robot can sit there like this. Right? And that will be the start position. And then we just do very simple ladder things. So we put another 2 here, and another 2 there, and another 2 there, and there, and there, and there, until you run out of the wall. And that would be, I think, the simplest. The simplest. There, you don't really need to calculate any motion plan, right? Because the plan will be 1, 2, 3, 4, right? And you keep doing this until you reach the top. So that one you don't really need any motion plan. And just simulate that in Mujoko. If it works, then you can build the rear wall. Then your little robot can climb the rear wall. And then from that we can go to, if you wanted to, you can make this one a right hole, and this one a left hole, for example. Because this will should still work, right?
For this type, the color is no, the same color. Right?
Yeah. You want to have, these ones should all be the same type of hole, should have the same color. So they should all be red, and this one blue, and this one green. Something like that. We should define the colors just so that it's easier for me to recognize what the holes are.
So we should also use for detection, color detection algorithm. Because I think in simulation it would work really good.
Yeah, but in the real world it won't. So you need to still figure out the contour, and that means even if you get the colors, right? You want to run the edge detection on that shape, and then open and close it to make it fill, and then figure out where the top straight line is that you think you can hold on to. Also, for the motion, I don't think you want your robot to move here and then latch on there, because there's quite a bit of noise usually in the position of your vision system that you detect the holes at, and there's noise in the motions in your servo control and everything, right? So I think what you want to do is, or what I would do is, you know the direction of the hole. So this would be a right hole. This is for the right hand. And in this case, you want to go off on the tangent to some point here, bring the arm there first, and then pull it in. Instead of trying to go right onto that edge with 0 millimeter error, I think it's better to assume that you have error, move it further off, and then pull the arm in. And the only thing that is not so nice, in simulation there's no problem, but with the real robot, unfortunately we don't have any torque feedback. So we don't really know if he has made contact with the hold or not. With the OP3 robot we can do that, and our large humanoid climbing robot can do that. But with the cheap RC servos, they have no torque feedback. So I was thinking about some way of doing that, but not one that would be cheap. And practical at the moment.
So how does the robot know? I mean, it needs to in this position for the first two movements for the lever problem.
Mm-hmm.
Like the first two movements, he only has to move like his arm to get here.
Yeah.
And then the other arm to get here. Yeah. But maybe the body's here and he can't reach.
Oh,
Then the leg, how does
that's
the robot
okay.
know
Then we
that
just
he has to pull up?
then we just do this. And he knows how to pull up because he knows the map.
So should the because it's easy to think of like one data group is only one link motion, but some movements would need several combined link movements. You know what I mean?
Okay, we don't do this. Like up and then latch onto two. No, we.
So we design the wall that there is
No. We limit the climbing.
That only one link moves at a time.
That we always have 3 points that are holding onto the wall. Like this case, these three. The center of mass of the robot has to be within this triangle, and then this joint is free to move. And that's the only kind of climbing we're doing. We're not doing dinos or topo or anything like that. But if we can do that, I think that already would be very, very cool. Like you can make a lot of paths like that. And actually the coach is already quite interested about that. They always, every time I go to the gym, they ask me about the robot and whether they can do a new path for us. Because if you look at what I did previously, this path, this is actually running the motion climber all in TypeScript, JavaScript, the motion planner. This path was actually done by one of the coaches there, that they're one of their route setters. So we have like a professional route there. So I didn't build this. I didn't build the path, I built the software to run this. Which is really important, I think, for robotics research, because we want to be able to show that our systems work without us over-engineering it and overfitting it to one particular problem. But this robot, this climbing robot here, if you look at it climb, it does exactly that. It moves one joint at a time.
But our robot won't be able to hold on to one hold with both hands?
Probably not, no. I mean, it depends on the kinematics that you implement, but it will be quite difficult. I mean, we can also change the holes. If you really want to match on a hole, I can give you a longer hole. we can make the holes a lot wider, so it's easier to grab on. But anyway, now I got this far, right? Now I have the positions. So now all I need to do is calculate the transformation matrices as, what is it, T folded by R. So T position is the transpose from the parent, R is the rotation relative to the parent. And my control variable is the rotation around the z-axis. So then we have the forward kinematics. Once we have the forward kinematics, calculating the inverse kinematics using the Jacobian approximation is also not too bad, because you take your current state, you calculate the forward kinematics, then you change each one of the joints by a tiny little bit, see how much your x, y, and z vector position changes, and then take a step into that direction. So if you look at the uh, climbing robot, if you look at the code here, and this is just calculating the forward kinematics, which is from the Blender file, that code. Now, where's my inverse? That's just forward here. So forward kinematics, then here is calculating the Jacobian, which simply goes through for each joint and changes it by a little bit, calculates the forward kinematics, gets the position, looks at the difference between those two, and divides it by some kind of step size, EQ here, and then inverse kinematics is, I thought it was like only 5 lines, but it's a little bit more. This is the whole code for the inverse kinematics. So we look at the current position and my target, and I calculate the current position in forward 2, and then my error, and oh yeah, so it's an approximation step. So then what you basically do is you check out how the value changes when you change joint 1, joint 2, joint 3, joint 4. Then you move joint 1, 2, 3, and 4 and 5 in, all in one step, a little bit in the direction that you think moves it closer to the target. But sometimes, let's say in the simulator, if there's an obstacle, then it's impossible to reach it. So in that case, you would end up, in your inverse kinematics, you'd end up in an infinite loop, right? So that's why I have a maximum number of iterations for the loop here. And I think it's actually not that big. I think I run like 20 of them. Or maximum number of iterations, I run 100. And this is running this in JavaScript in real time. Like every time it moves a joint, that's what it calls. So it's easily fast enough for, because TypeScript is not even such a fast language, right? So here we'll just do that. So anyway, inverse kinematics is basically this. And this works, okay, like I've used that approach. And only if I have specific requirements do I even try and come up with something smarter than that. Because the nice thing about this is that it comes out of the Blender file directly, so I don't really need to. This code here for inverse kinematics is completely independent of your robot. Like this will work on your robot, or anybody else's robot. So that's kind of cool too. Oh, they have a new BB link now. Oh man. IEI 3DU VAA 1ZU. Okay, but I connected there. Nobody here. Hello? Oh no. Okay, good. Then I can stop the recording. I think we're done, yes? Let me just